Okay, in this problem, we talked about carnival rides that go in a circle. So this was about centripetal acceleration. So let's call this carnival rides in a circle. And, we can start with the simplest ride, like a merry-go-round on a playground, let's say. And you can have an object sitting on a surface and going around in some speed. And so for each of these problems, we were given some radius r, right? So if you're at some distance r from the center of the ride and the ride is traveling around in some speed, let's find a safe speed. So r is given, and we're going to find v. Okay, so for this first problem, this is sort of problem 0. Our free body diagram looks like this. We have a normal force upward and a friction force. Now the friction force operates against the way you would go if you were slipping. And so the friction force, the maximum friction force, looks like this, and then an mg downward. And your acceleration inward, not a force, but your acceleration is v squared over r. And so if we write the free body diagram here, we choose axes that look like x and y, and we draw then, or we write that the sum of the forces in the x direction is mu s times the normal force, and that's m v squared over r. The sum of the forces in the y direction is Fn minus mg, and that's equal to 0. And so this tells you then the second equation here says that Fn is equal to mg, and so that means that mu s, by rewriting the top equation, times Fn, which is mg, is mv squared over r. So, let's try that again, v squared over r. The m's cancel, and what you find out is that the v is square root of mu s g r. So that's kind of the simplest going around in circle. But then we tried another ride. Then we tried the kind of ride where instead of on a flat surface, this is actually a cylindrical ride. Somebody said it was called the gravitron. And the object now sits against the wall, and what makes it exciting is that the floor falls away and it's going around in a circle. So if we repeat this now, what we find is that, the force in the first example, that was the force that was inward pointing, was friction. Now the force that's inward pointing is the normal force. So the mathematics are going to look the same, very, very similar anyway, and even the free body diagram starts to look a little bit the same, only now things are switched, right? Now friction, the friction that was inward is now upward. So we have the force of friction times the normal force, and now it's the normal force that goes inward, and mg is down. So once again, we have a centripetal acceleration of v squared over r, where your distance from the center of the thing is r, and the sum of the forces in the x direction, let's choose the same axes, is this time the normal force is mv squared over r, and the sum of the forces in the y direction is mu s times the normal force minus mg is equal to 0. So now this second equation tells us that the normal force is mg all over mu s, which means from the first equation mg all over mu s is mv squared over r. The m's cancel, and now v is the square root of gr divided by mu s. Notice how simple it looks.
Yeah.
and how similar it looks to the previous one, but of course this is a very different ride. And finally then, we said, what about a ride that's a loop-de-loop, like on a cart? So if you have like let's imagine you're in a car and it's on a track, and here's the box, right? Now what's going on, right? In fact, you can even imagine a super slippery track, and we'll just put the box just like this. There we go, there's the track. So now, right, now your free body diagram is such that, once again, distance from the center is r. Now you have gravity downward, mg, and maybe there's a normal force, but really you don't even need a normal force to go around in a circle for this ride. So as the normal force goes to 0, that gets pretty exciting because it feels like you're just hovering, right? Because now there is no normal force between your rear end and the seat. So in fact, all you really need for this ride is just using gravity. So before we saw friction being the inward force and then the normal force being the inward force. In this case, it's just gravity. The sum of the forces here, mg, that's the only thing that needs to be the centripetal force, mv squared over r. And so this is particularly simple. V is the square root of gr. So notice now that we have 3 different cases, right? We have v is equal to the square root of g times r. And then in the previous 2 examples, we had a mu s in there. One where the speed could be less than gr, one where the speed could be more than square root of gr. But I think all 3 of these problems go together.